Hello everyone. Before we begin, can you guys all hear me clearly? If you can, just let me know in the chat and we can get started. Yep, alright, cool, thank you. So, welcome to the second part of the Math2400 workshop. So, on Tuesday, Jordan went over the first 4 topics. So, he went over the integers and natural numbers, representation of numbers, modular arithmetic, and powers of roots. Today, we'll be covering the second half of the course, so mainly going into cryptography, polynomials, and we'll finish off the course with some study on finite fields. And sort of the reason why we want to look at finite fields is because we want to develop the theory behind developing codes that are capable of correcting more errors. And that's really looking at things like BCH codes. And so that's the plan for today. All right. So let's go over part 5. So this first chapter is really just an introductory chapter to the theory behind cryptography, modern day cryptography, and a look at coding theory. All right. So the point with cryptography is really 3 things. The first thing is you need to be able to, or given a message, you want to be able to encode the message so that other people can understand it. But at the same time, when you're given a message from some channel, you need to be able to decode the message. But these 2 aren't enough because if you just encode the message, anyone can intercept it, and if they can understand it, then there might be some problems. In the same way, if you just only decode the message, then you may run into some problems, because if that message is it needs to be secured, then you'll run into problems. So the last thing is we want to be able to correct messages, because sometimes when you send messages through a channel, that encoded message may not be correct. There might be some corruption happening in that channel that forces the message to be incorrect. And so these 3 things really form the basis for cryptography, modern day cryptography. All right, so we'll be looking at specifically some ideas behind how you could create a system to encode and decode messages. And at the same time, we will also develop 2 fundamental systems for what modern day cryptographers do. So the basic idea with encoding and decoding is that if we encode the message and then we decode that encoded message, then we should receive the same message, ideally, right? Because if you just encode it and then you decode it, you really should get the same message in the end. So, for example, if we look at a way to encode the message by taking any message x, and you map it to x to the power of 7 in modulo 26, then your decoding function would also be x to the power of 7. And this is really the basis for what we do in RSA, which we will look at in the next few slides. But the first thing we're going to do is we're going to look at an error correcting code. Namely, we're going to be looking at the Hamming code, and then we're going to use that to then kind of think about how we might like to model RSA. So an error correcting code is really just a code that can correct and subsequently detect errors. So if I give you a message, if we have an error correcting code, that means that code should be able to correct the message if there are some errors, and then we should be able to decode it. And that's really all error correcting codes are. So some examples of error correcting codes would be the repetition codes. So for example, if I give you a bit, say 1, the idea with the triple repetition or the 3 repetition code is that you need to send it 3 times, and I will take the majority, and that would be my encoding system. There are some other error correcting codes, and we'll be looking at the Hamming code. So the standard Hamming code is really just a code where you use a matrix, and then you multiply that matrix with some message. And at the end, you'll get some vector. So this is just basic linear algebra. So if you're given a 3 by 7 matrix, and then I give you an encoded message, you should get some vector in the end. So the Hamming code is really just a code in which you use the Hamming matrix, and this Hamming matrix is really easy to model as well. So the last row represents 2 to the power of 0. The second row represents 2 to the power of 1, and then the first row represents 2 to the power of 2. So if you look at the first column here, the first column is represented by 0, 0, 1. But 0, 0, 1 is just 1 in binary. If you look at 0, 1, 0, well, this is 0 times 2 squared, which is 0, plus 1 times 2, plus 0. So the second column is the binary representation for 2. This is the binary representation for 3, 4, 5, 6, and 7. So the Hamming code or the Hamming matrix is really just a matrix in which the columns represent the binary expansion. Yep. So once we develop that matrix, then we can sort of send the original message, and we want to encode it in this way here. Now, this is specifically for this specific Hamming code. We can obviously change rows, or we can change the columns, so we can interchange, say, these 2 columns around, and then we will have a different encoding system. So the way that you want to think about encoding it is your X, your Y, and your Z, they are what we call the check bits, and then the A, B, C, D are your information bits. So the information bits, they hold some information that we want to encode. The X, Y, Z are just pretty much filler. So they are filler because we want to ensure that we have enough bits to be able to multiply by H. So X, Y, Z, they are really just the components in which the columns are leading. So if you look at this matrix, then you see that this one is leading, this one will be leading as well, and this one will be leading, depending on how you rearrange some of the columns. So you can see that this one's leading. Since this one's leading, this one is leading, and this one is leading, these will represent your check bits. So you can see that if I take a look, I guess I'll highlight it. If I take a look at this, your X here will represent the first column. Your Y would represent your second column. And then your Z will represent your fourth. And that's how you can encode this message. So you can encode this message here. So the information rate of this, usually with Hamming codes, it's always the same. So for a standard Hamming 7.4 code, the information rate is really just 4 divided by 7, because it's the number of bits in the original message, which is 4 here, divided by the number of bits in the encoded message, which is 7 here, because you have 4 information bits and then you have 3 check bits. Cool. If I'm going too fast or if there's anything that you're unsure about, just type it in the chat and I will try and answer them as promptly as I can. Cool. So there comes a question then. When can we possibly have an error in your Hamming code? And well, we have an error if h of c is not 0. So when we multiply, say, this vector here with h, if it's not 0, then we have an error somewhere. And the result of this will tell you what column the error will occur. So if, for example, if h times c was, say, I don't know, the last one, then there is an error in the last bit. So here in your last bit, in your encoded message, your D would be incorrect. And so you have to change your D. Cool, so we'll go over some examples of how you might like to encode and decode Hamming codes. So this one comes from the 2016 paper. So we have a standard Hamming code. So this is just your standard Hamming matrix. And we know that the message, some message A, B, C, D, is encoded by your standard encoding system. So X, Y, Z, they are your check bits, and then A, B, C, D, they are your information bits. So the first question is, what is the information rate of this code? So this one you should be able to write straight away. So I guess I will. So the information rate of this code is really just the number of bits in the original message divided by the number of bits in the encoded message. So you should be able to just write it out straight away. There is no need to do any work. You just have to write it out. Okay, and I do go over that. Yep. So the information rate here is just 4 divided by 7. And you should expect that with a Hamming code, because the Hamming code is really the same every time. You always have 4 bits, and then you encode it using a 7-bit matrix. All right, so using this sort of system, we want to encode 0, 0, 1, 1. So how might we want to do that? Well, the first thing we know is that 0, 0, 1, 1 is what A, B, C, and D are, right? So we already know what these values are. And so all we need to find is X, Y, and Z. That's all we need to find. So whenever we encode it, we already know 4 out of the 7 bits. We just need to figure out what these check bits are. Well, using the theory that we had before, we require the H times C to be 0. So using this, well, we can use the fact that we know that the encoded message will look like this. So it will look like this. And all we need to find is X, Y, and Z. Well, another good thing about this Hamming code specifically is that we are working in mod 2. So if there is, I'll get to it in a bit. So if C is a code word, then HC is equal to 0, right? That's just by definition of what the Hamming code is. Okay, so let's just multiply this. Well, if we do X times 0, you get 0. The first 3 terms will be 0. The very first term you get is Z. Z multiplied by, so Z plus 1 times 0, plus 1 times 1, plus 1 times 1. So in the first in the first element here, you should get z plus 2. But remember that we're working in mod 2, so z plus 2 just amounts to just z, because 2 here is the same as 0. Okay, so let's do the same thing with the second term. So we're going to multiply everything here by this vector here. So we get 0 times x plus 1 times y. So we have a y here. 1 times 0, 0 times z, 0 times 0, and again we have 1 times 1 plus 1 times 1. So again you'll get the same thing. Plus 2. But remember, plus 2 is the same as plus 0 in modulo 2. Okay? And the last thing we're going to do is we are just going to multiply the last row with the column, with the vector. So 1 times x gives us x, 0 times y gives us 0, 1 times 0 gives us 0, 0 here, there's a 0 here, 0 here, 0 here, and the last terms would be a 1. So you get z plus 2, y plus 2, and x plus 1. But remember that these terms they vanish because we're working in mod 2. So if this was an encoded message, then this term here would be 0, will need to be 0. Which means that we need each of these elements specifically to be 0. Well, the only way for z to be 0 is if z was 0. Similarly with y has to be 0. Then x plus 1 needs to be 0. But remember that we're working in modulo 2. So if we just say x equals to 1, then we have that 1 plus 1 equals to 2, but that's just 0. So we've now found our x, y, z terms. So now we can finish our encoding. So now we have x, y, z, a, b, c, d. And then we can encode this message here. And the encoded message just becomes this. So this term here is your x. This term here is your y. And this term here is your z. So once we know that, then we are done. And we can just encode it. Cool. Now, we will go the other way and we will try and decode the message. So in the previous example, we encoded a message. This time we're given the encoded message and then we're going to see if there's any error. And if there is, we'll fix it and then we'll decode it. So the first thing we do is this a code word? Well, the only way for it to be a code word is if h times this vector here is equal to 0. So let's check that. So the first thing we need to do is to check to see if hc equals to 0. Well, if we just do our standard matrix multiplication, then we can see that we get this long vector here. But if we just look at the simplification for this, the 1 and the 1s will vanish because they add up to get 0. So all of that will vanish to 0, and we're left with 1. Similarly, these two guys will vanish to 0, and finally these two guys will vanish to 0. So all we are left with is 1. Whoops, let me erase this. So we are left with a 1 here, whoops, a 1 here, oh my god, and then we don't get any terms here. So we are just left with 1, 1, 0. And you can see that this is not 0, right? Because for this to be 0, every term here needs to be 0. but clearly 1 is not 0. So we can see that there is an error. And the way to know that which column is the error, we just look at this matrix. Remember, this is your H. And then we can see that the expression that's the same is this term here. So what does that mean? Well, that means that if we go back to our previous slide, that means this term here was wrong. And so that means, because remember, we're working in modulo 2, so this term will get flipped to 0. So the correct encoding should be 0, 1, 0, 0, 1, 0, 1. And so once we know that, then, well, we can easily decode it. So the decoding is just 0, 1, 0, 1. And the way to know that, to know what the decoding is to just look at A, B, C, D. So A here is 0, B here is 1, C here would be 0, and D would be 1. And that's what you get. Cool. Another example. So the first part, explain how the ith column of H is constructed. So as we kind of explained before, the ith column is really just the binary representation of I, right? So the third row, it represents the coefficient of 2 to the power of 0. The second row represents the coefficient of 2 to the power of 1. And the first row represents the coefficient of 2 to the power of 2. So that's how you can construct the H. Cool. So for part B, the information rate of this code. So the way to remember that the information rate is just the ratio of the number of bits in the original and the number of bits in the encoded message. So the original message has 4 bits. The encoded message has 7 bits. So the information rate is 4 divided by 7. And again, you should really expect that. That should be, you shouldn't really need any working out for this. You can just write it out because it's pretty straightforward. All right, so again, we're going to encode something and then we're going to decode something. So remember, to encode something, we already know 4 of the bits, and all we need to do is find what X, Y, and Z are. Then for the decoding part, we check to see if this is a code word. If it's not, then we can detect the error and we can fix the error. So the encoded word is X, Y, A, Z, B, C, D. And we already know what A, B, C, D are. That's given to us in the question. So A, B, C, D is just 1, 0, 1, 1. So C, in this case, would be X, Y, 1. So X, Y, A, Z, and then B, C, D. So that's how we can encode C. And then we solve HC equals to 0. So it gives you this. Remember that we're working in modulo 2. So this guy vanishes to 0. This guy also vanishes to 0. And this guy vanishes to 0. So once we know that, then we know that our final vector here would be z plus 1, y plus, that's z plus 0, y plus 1, and x plus 0. And so we just have this. If we want to set it equal to 0, then we need each of these components to be 0. So z has to be 0, y has to be 1, and x has to be 0. And we're done. We have encoded our message, and then we can also decode the message as well. All right, so part D. So we need to decode the message and check to see whether this has any error. Remember, we assume up to one error. So there could be no errors, or there could be one error. You won't have a case where you have two errors because this code is too weak to correct two errors, or even detect two errors. So the first thing we need to do is to check whether this is true. Well, we can see that if we just multiply this matrix with this column vector, we get 1 plus 1, 1 plus 1, and 1. Clearly, that's not the 0 vector. So we know that there is an error. And in particular, we know the error is in the first value. And the way we know it's in the first value is because this vector is located at the very first column. So we basically just match up the columns, and then the column will tell us where the error is. And so we can decode it. So to decode it, you really just look at A, B, C, D. Well, the error is in the check bit. So that doesn't really matter to us, because if an error is in the check bit, then we're okay. We're only worried if the message, if the error is in one of the information bits. But because it's in the check bit, then the decoding part would just be this. And so we're done. Yep. Cool. Okay, so that was the Hamming code. So the Hamming code is a very useful kind of cryptographic system, but it's not that good, right? Because if there are two errors, we can't really detect, or we can't really correct them. We might be able to detect them, but we can't really correct them, and that's a problem. We look at another type of cryptographic system, and this is called the RSA Code. And this is really founded by 3 scientists or mathematicians. And RSA is named after them. So RSA are the initials of the mathematicians who came up with this system. And this really relies on the fact that factorization of integers is incredibly difficult. It's incredibly time consuming, and many people just would stop after a certain point. And so this is a very secure way of encrypting and decrypting data, and quite a lot of modern day cryptographic systems actually rely on RSA. So the input that we give to an RSA code is some message. It has arbitrary length m, and it doesn't have any more than n digits. The algorithm for RSA is as follows. We arbitrarily choose primes p and q large enough so that the product is greater than 10 to the power of n. And this is sort of arbitrary, because the reason why we want it to be 10 to the power of n is because if it's anything less, then we will be able to develop an algorithm to efficiently fish out all of the primes. And we want to independently choose your primes. Your primes shouldn't follow some specific pattern. And we'll see later on why following a specific pattern is not a good idea. So once we choose your primes, that is going to be your private information. You should not let anyone else know what your primes are. The next thing you want to do is to compute the Euler phi function of n. Remember that P and Q are primes, and they are large enough so that this product exceeds 10 to the power n. Well, P and Q are prime, so that means the phi function of n would just be the product of P minus 1 and Q minus 1. Your phi function should also be private, and it is private by virtue because of the fact that P and Q are private. Okay, so once you compute the phi function of n, then you want to choose some encoding power, s, such that the GCD of s and the phi function is equal to 1. S here can be made public, so the only things that are public are the powers, or the power, and n. Everything else is kept private. So you choose a power s such that the GCD is equal to 1. And then to decode it, you want to find the specific t such that s times t is congruent to 1 modulo phi. So it's really a three-step process. You arbitrarily choose your primes, so you independently choose your primes, P and Q. Then you compute the phi function of n, and you want to choose some power s such that the GCD is equal to 1. And in the third step, if you want to decode it, you just have to find the value t such that the product is congruent to 1. In other words, t is the inverse of s in phi of n. Okay, so our encoding function is going to look like this. So you take a message m, and you want to encode it using m to the power of s modulo n. And then to decode it, you want to take your message and you want to raise it to the power of t. Remember that the power of t is just the inverse of s. So if you combine the encoding and the decoding functions together, you should ideally get back m. And that's what you do. Yeah. Cool. So, can you elaborate on the part of this that makes it so hard to crack? Okay, sure. So, the reason why RSA is so difficult to crack is purely because it relies on the fact that integer multiplication or integer factorization is incredibly difficult. It's an incredibly difficult problem, and it's actually NP. It's an NP problem, meaning that if I give you I can't develop an algorithm to be able to solve it. But if I'm given a solution, I can verify quite easily, in polynomial time at least, whether or not the solutions are correct. So it's hard for me to solve it it's hard for me to find a particular algorithm to solve it. But if I'm given a pair of integers, I can verify quite easily whether that is the correct solution. And so the whole idea with RSA is that non-deterministic polynomial algorithms may not necessarily be polynomial time algorithms. So this is the whole problem, the whole idea with is P equal to NP? If we can develop a polynomial time algorithm to crack RSA, then that's the idea of integer factorization becoming a polynomial time algorithm. So we'll be able to crack integer factorization in polynomial time. But the unsolved problem of P versus NP allows RSA to be somewhat secure. So given n, it's too hard to find P and Q to generate decoding function. So if you were someone who was a cryptographist and you only know n, well, if we take some number, I can give you an arbitrarily large number. Let's just say 3 million. 3,001,111, 3,001,111. Can you easily find factors of this? So can you easily find prime factors for this? Well, I've arbitrarily picked this, but the story goes that if you give me a really large number, it's really hard to find your particular primes, because the distribution of primes as you go further and further out is, well, we don't know that yet, right? That's the whole idea with number theory. We don't know the distribution of primes. So if you give me two really large primes and then you calculate the product of them, that's an incredibly large value for n. And to be able to efficiently find your primes p and q, if I was only given n, well, that's going to take quite a long time, because we don't actually have a system, we don't have an algorithm yet to be able to efficiently look at all of the prime factors. And because there's so many primes to cover, it's not very efficient. And that's why RSA is quite secure. If we were able to crack integer factorization, then RSA will be virtually useless. Yeah, I mean, you could also give it some larger and larger numbers. But the idea is that it's going to be increasingly more difficult to find your prime factors. So that's the idea with why RSA is so difficult to crack. With that said, it's not impossible. I guess you could... is S the public part of the... So both of these, so N and S are both public. So N here is public. Oops, that's draw. Highlight. So N here is public. S here is also public. So these two are the only public ones. And the idea is that if you give someone P and Q, and then you also give them S, then they'll be able to find the decoding part here. The reason why T is difficult to find is because we don't even know what phi of n is. If we're given an n large enough, then we can't really find what phi of n is, or at least it's very difficult to find phi of n. And so as a result, we won't be able to find T, because T relies on phi of n. But because phi of n depends on P and Q, and it's hard to find P and Q in the first place, that's why it makes it difficult. We'll go over an example why P and Q need to be independently chosen. Because if P and Q follow a specific pattern, then we can easily crack it. And we'll give an example of that coming up. Okay, so hopefully that sort of... so phi of n can only be calculated by finding factors. Exactly. So because it's so difficult to find what P and Q are, it's so difficult to find phi of n, which in turn makes it difficult to find what T is. Cool. All right, so for this part, we want to compute the phi function of 323. And we're given the factorization of 323. So 323 is 17 times 19. So it's quite easy. Phi of 17 times 19, which is just phi of 17 times phi of 19. But because these two are primes, let's just set 16 times 18, which is 288. Okay, so the second part, does the function m mapping to m to the power of 10, sending a message m to the residue m to the power of 10, give a valid RSA encryption? So remember that what we needed to have here for the encoding part was that the power s that we choose needs to be relatively prime to the phi function that we compute. So the suitable values for the power needs to be relatively prime. But if we look at this, 288 and 10 here, well, they are both even at the very least. And so because they're both even, at least we have a GCD of 2. And so what we have in the end is that the GCD is not 1. So 10 is not a suitable power. And the reason for this is because the value for t won't be defined. So the reason why we choose an S to be relatively prime to phi of n is because that allows us to find a unique inverse, which is the value of t. But because they are not relatively prime, nope, there won't be any power of t, or suitable power of t. So 10 won't be a suitable power at the very least. Cool. And this is just the same thing. So we want to find the phi function 143. We're given we know 143 is just 11 times 13. They are both relatively prime, so we can split up into the multiplication of the phi functions, and that's 120. So that's 10 times 12, which is 120. Okay, so first of all, we check 7 and 120 are relatively prime. So 7 is a suitable power for is a suitable encoding power. So to decode it, we need to find an x such that 7x is congruent to 1 mod phi of 143, and we've already calculated this to be 120. So we need to really look at how to compute this. Well, there's no easy way to do it. We just have to do it one by one. So we just find the inverse of 7, and the inverse turns out to be 103. So you can check it yourself. So you kind of have to go through one by one. There might be some shortcuts, but you could also just use a online calculator if you really wanted to. And I think it's because anyway, the inverse is 103. So an appropriate decoding function is just m mapping to m to the power of 103, taking the modulo 143. Cool. I'm going to skip this. This is really the same thing. I want to go over this question because this question illustrates why we need to independently choose P and Q. They shouldn't follow a specific pattern. So let's look at this. An RSA code has been constructed using the modulus m equals to PQ, and PQ here are primes of this form. So we know that the primes are of a specific form, and then we want to be able to design some strategy to use this information to break the scheme, and then we want to explain it on the example m equals to 33,667. So I looked at this question, and well, the first thing I noticed is that, well, m is 2 to the power of k plus 3 times 2 to the power of n plus 1. So let's expand that. So the only thing we know about this RSA problem is we know m, and we know P and Q are of this form that's given to us. So we know that m equals to 2 to the power of k plus m plus 2 to the power of k plus 3 times 2 to the power of n plus 3. So that's just what happened when you expand this. Well, notice that we have a lot of 2's here. So our goal here is to really write m in its binary expansion. And the reason for this is because we want to be able to find a way to extract our k and n. So we want to be able to find this, and this. And if we can find it, then we're pretty much done. So we will try to explain how we might like to break this scheme on 33,667. So the first thing we know is that if we write m equals to 33,667, well, we're basically going to find the highest power of 2 that is smaller than m. And it turns out that the power that is smallest, the biggest power that is smaller than this number is 2 to the power of 15. And then we subtract, and then we keep going down this path, and then we eventually get this factorization here. So 2 to the power of 15 plus 2 to the power of 9 plus 2 to the power of 8 plus 2 to the power of 7 plus 3. So what does this mean? Well, the 3's here are in common, right? If we write it in this form here, the 3's here are in common. So we can just eliminate them, and then we're left with 2 to the power of k plus n plus 2 to the power of k plus 2 to the power of n plus 1 plus 2 to the power of n, and that equals to this expression here. So what does this mean? Well, if we assume that k and n are positive, that means k and n is the largest power. So at the very least, we know that these two guys must match, because we assume that k and n are positive integers. So we want to find some combination of k and n so that when you add them together, you get 15, but it also follows this pattern here. Well, if you look at this form here, we can kind of see a little pattern here. So I will use... So we know we have an n plus 1 here. And we know we have an n here. So what this means is that n could either be 8, in which case n plus 1 will be 9, or n could be 7, in which case n plus 1 would be 8. So let's consider these two cases separately. So if n equals to 7, so we'll start off with 7. So if n equals to 7, then we know n plus 1 equals to 8. So we have these two guys now. So this guy here is this guy, and this guy here is this guy. And so what that leaves is k equals to n. K equals to 9. But notice that 9 plus 7 is 16. And 16 is not 15. So, well, this can't happen. So this cannot happen. Which leaves us with the other case. So n equals to 8, in which case n plus 1 equals to 9. And that leaves us with k equals to 7. And we check. N plus k is, well, 7 plus 8, and that's 15. So we have k and n, which implies that we have this form now. We have this, and we also have this. So you can see that by picking p and q in as specific integers or specific forms, we can at least develop a way to crack the RSA code. So this is why it's important to independently pick p and q, and they shouldn't be following a specific form, such as the Mersenne prime. Yeah, cool. And this cracks the code because we are given p, or we already know p and q, so we know p and q, which implies that we know phi of n, or phi of m, which implies that we also know t, because we're given the power s. So we're given m, we're given s, we can find p and q, which means that we can find phi of n, m, which means that we can find t, which means we can crack the code. Cool. Does anyone have any questions regarding that? I probably went a bit fast, but it's not too hard to kind of grasp as well. And that pretty much finishes the first chapter, which is cryptography. So just to summarize, we went over two specific codes, the Hamming code, and then we went over the RSA code. How would this break twin primes? Okay, so let's take a look at twin primes. So I guess I'll do it here. So say that we have let's pick black. Oh my god, my handwriting is going to be so bad because I'm doing it with the trackpad. And so let's just say we have a prime P, and we also have a prime Q. And because they are twin primes, Q must be of the form P plus 2. Alright, so what that means is that M, remember that M equals to the product of your primes, right? So P times Q. But what is Q? Q here is, Q here, I'll write it here. So here, I'll write it down here, sorry. So, what this means is that M equals to P times P plus Q, P plus 2. P plus 2. But we can also write this as P squared plus 2P. Oh, P squared. Oh my gosh. Okay, let me rewrite this. I apologize for this. My trackpad skills aren't great. P plus 2P. Alright. So from this, we can complete the square. And the reason why we want to complete the square is because that allows us to find a way to find P. So P squared plus 2P is the same as P plus 1. P plus 1 squared. Well, if we square it, we need to subtract 1. So remember, this right-hand side is equal to whatever M was. And we are given M in the first place. So the public knows M. So we know M is of the form P plus 1 squared minus 1. Okay? Now, we can just add 1 to both sides, take the square root, subtract 1. And we have an explicit form for N, or for P. So M plus 1, we take the square root, and then we subtract 1. And that will be your value for P. And because you know P, you also know Q, because, P is P, and then Q is P plus 2. Cool. Alright, I guess I could take a break here, and then we'll move on to polynomials and finite fields at 4 o'clock, 4 p.m. If you have any questions, feel free to ask now, and then we will resume at 4 p.m. I have a question here. So why do we find S for RSA such that GCD? So do you mean why specifically do we require S to be relatively prime? So if we look at this, right, are you saying why do we specifically say S to be relatively prime to a phi of n, or why do we find, well, what's the point of the prime, or the power? Okay, so I'm assuming you want to know why we require GCD to be 1. So I'll go back to a previous topic that we did. So remember, the whole idea is that we want to be able to construct a T such that this holds. So why relatively prime? So remember that the whole idea is that we want to be able to find a T such that ST is congruent to 1. Well, let's go back to a previous topic that we did. Let me find it. So if we go to, oops, I think it's one part here somewhere. Oh, it might be it might be in the previous topic. So one thing we know is here. So this is probably the most important result. So inverses can only exist if the GCD is equal to 1. So if I gave you the GCD of A and B, oops, if they weren't 1, if they were not 1, what does that mean? Well, that means that A and B can't, well, there is no inverse for A in modulo B. Yeah, cool. So we require that the GCD to be 1 for there to be an inverse. And if we know the inverse, then we're able to find this T. Because remember, the T is the inverse of S. Cool. If not 1, then we can't find. Yeah, so the idea is that the inverses can only exist for if the GCD is equal to 1. So if the GCD was not 1, then this whole algorithm breaks, because we can't decode it. There's no way to be able to decode the message, which is why we restrict our thinking to the GCD being 1. Cool. All right. I guess we'll get started again. So we're going to be going over polynomials, and then we're going to kind of cover finite fields towards the end. So I guess the way to kind of introduce polynomial rings is to really just make some analogies to what we've already studied back when we did integer rings. So let's kind of compare the relationship between, say, Zn and the rings, the polynomial rings. So the elements in X modulo, or the elements in Zn are the elements modulo n. On the other hand, the elements in this polynomial ring are just polynomials with coefficients in R. So this R is not restricted to just fields. You could also have things like Z4X, so these are rings. And really what this means is that you construct a set of polynomials with coefficients in this ring. So this is your modulo 4 ring. And if you just slap an x here, that means that you're constructing what we call a vector space over this ring. But this is really just a polynomial. So this is just a ring of polynomials with coefficients in, say, Z4. But you can extend this to Zn. You can even have Q, the rationals as well if you wanted to. So we say R to mean a very arbitrary or a very general description, as a very general description. Well, the identity is just the 0 element in Zn. But remember that the elements in Rx are polynomials. So your identity polynomial would be the 0 polynomial. So every coefficient is 0. And similarly, for the identity, in the multiplicative identity, your element will be 1. In the polynomial one, you have p of x equals to 1. So that means you have a constant 1, and then every other term would be 0. And the good thing about polynomial rings is that it pretty much works in the same way as integer rings that we've already seen. So anything that works in Zn will also work pretty much the same as Znx. The only difference is that you have different ways of describing the same idea. So we'll look at things like the greatest common divisor, and we'll look at some other things. But polynomial rings are not that much different to integer rings. Cool. So the greatest common divisor between two polynomials is just a polynomial. So much like when we looked at integers, the greatest common divisor of two integers is just an integer. In the same way, the greatest common divisor between two polynomials, call it f of x and g of x, is just a polynomial. It's just a polynomial that factors into both of them. So we call them common divisor. And any other factor polynomial, q of x, is a factor of the GCD. So this is what we mean by the greatest. If we compare this to our previous definition of the greatest common divisor, you would have seen C, or maybe not that color. Maybe I'll just do black. Black is easy, or I'll do red. Red is quite nice. So back when we did integers, we said C was greater than or equal to D. That was when we looked at integers. But we don't have the notion of less than or equal to anymore. Instead, we look at factorization. So we say that it's the greatest if any other common divisor also divides into the GCD. So it's a common divisor in the sense that it divides into both f of x and g of x. And it's the greatest in the sense that any other polynomial that divides into both of them has to also divide into the GCD. So the good thing about the greatest common divisor with integers is that it's a unique integer. But we don't have that notion of uniqueness anymore because we have this scalar multiple happening at the start. And multiplying by just a scalar won't change anything about the roots of the polynomial. So if d of x is the greatest common divisor between f of x and g of x, then so is any scalar multiple of d of x. So you don't have the uniqueness of greatest common divisor anymore. In the case of integers, you had that, but in the case of polynomials, you'll have a set of greatest common divisors, and you can enforce it has to be a monic polynomial or it has to have some special property. So we're going to find two polynomials, a quadratic polynomial and a cubic polynomial ring. So it's just the set of polynomials with integer coefficients. So z is just integers. So we're going to find a quadratic polynomial and a cubic polynomial whose greatest common divisor is x. So there's a few ways to do it. You can kind of check and guess, but a way to kind of systematically do it is as follows. What we're going to do is we're going to construct these two polynomials. So we're going to let f of x be the quadratic polynomial, and then we're going to let g of x be the cubic polynomial. But we know that the GCD is x. So what that means is that we can use the first property here to say that x must divide into f of x, and x must divide into g of x. Okay, so we have this result. We have this result here, and we also have this result here. So we have the fact that x must divide into f of x, and x must also divide into g of x. Alright, so we can write f of x in this form. Remember that we have f of x equals to x times ax plus b. And similarly, because we know that g of x is a cubic polynomial, this term here must be a quadratic. Alright, now the next thing we're going to use is the fact that x is the greatest common divisor. So it's not just a common divisor, but it's the greatest common divisor. So what does it mean for it to be the greatest common divisor? Well, the other terms here must not divide into one another. Well, certainly cx squared plus dx plus e can't divide into ax plus b because the degree of this polynomial is greater than the degree. So we need to have that ax plus b cannot divide into cx squared plus dx plus e. Otherwise, we have another factor and x is no longer the greatest common factor. So we can arbitrarily pick values for a, b, c, d, and e such that this is not true, or this is true. But keep in mind that a cannot be 0 and c cannot be 0. Otherwise, you no longer have that quadratic and cubic polynomial that we are supposed to have. So we also impose the fact that a and c can't be 0. Well, if we set all of them to be 1, then, well, we get x plus 1, and then we get x squared plus x plus 1. Well, x squared plus x plus 1 doesn't have any linear factors. If we look at specifically polynomials in Zx, x squared plus x plus 1, this term here can't divide into this term here if we set all of them to be 1. And so we obtain x squared plus x cubed plus x squared plus x. And you can check that these two indeed will have GCD of x as x. And you can check that by just dividing g of x by f. These two polynomials specifically so that they have GCD x. And so by virtue, their GCD must be x. Hopefully this sort of argument makes sense. How you could possibly force the other terms to not be factors of one another. And that's how you can guarantee that the GCD must be x, or whatever you want it to be. Cool. Another example, we want to find a polynomial of degree 4 whose greatest common divisor with this polynomial is x times x plus 1. So again, we are going to do this constructively. So the first thing we notice is, well, we're going to just set f of x to be the degree 4 polynomial. And it's a polynomial in Zx, meaning that it's a degree 4 polynomial with integer coefficients. Well, if we look at this, right, we notice that x squared times x plus 1, well, that's the same as saying x times x plus 1. I think I wrote it down somewhere. Anyway, so yeah, so x times x plus 1 is the greatest common divisor, meaning that x times x plus 1 must divide into f of x. So this is the first condition that we have. And so what that means is that we can write f of x, remember it's a degree 4 polynomial, so we can write it as x times x plus 1 times some arbitrary quadratic. Cool. Well, it's the greatest common divisor, which means that x can't divide into this portion here. And the reason for this is because the only remaining term here after you quotient out x and x plus 1 at the start. So we know x can't divide into this remaining term here. And so we can randomly choose A, B, and C such that it's not true. Well, the easiest case is to look at x squared plus 1 because it doesn't have any roots in zx. And so what this means is that this polynomial is the polynomial that we constructed, which guarantees that we have this GCD here. And again, we just constructed using the properties of the GCD. Cool. So now we go on to this really important concept. It underpins everything else that we do from this point on. So I'm going to really drill this in on you. The irreducibility is probably the most important part of this whole chapter. So a polynomial p of x is said to be irreducible in this ring if we cannot factor p of x into a product of polynomials of smaller degrees. And that makes sense, right? So we can't really write it in as a product of polynomials if it's irreducible. That's what it means for it to be irreducible. So one way to check whether a polynomial is irreducible is to look at what we call Eisenstein's criterion. And this is really an important test, but it's not a sufficient test, or it's not a necessary test. So if a polynomial satisfies this Eisenstein's criterion, indeed it is irreducible. But just because it doesn't satisfy it doesn't mean that it's not irreducible. It can still be irreducible and still not satisfy this criterion. So we consider some polynomial p of x. If we can find a prime number p that divides into every coefficient except for the leading term, and the square of that prime does not divide into the constant term, then p of x is said to be irreducible. So we'll go over some examples with Eisenstein's criterion just to get your head around what this means. Let me see if I have an example actually. I might, okay. I would do an example here. Okay. We will go over some examples later on. I want to cover 3 more techniques that we did in class as well. So we're going to kind of hone at if we consider some polynomial, if the GCD among all of these coefficients is 1, then we call it primitive. So this kind of is important for technique number 1. So if p of x is a primitive polynomial of degree n and is also reducible, then indeed it must have a factor of degree n divided by 2 or less. And that makes sense, right? Because if we consider some polynomial, we multiply it by another polynomial, say of higher degree, then at the very least, the sum of degree n divided by 2 or less, just a factor. Technique number 2 is saying that if you have some root, so r divided by s is a root of this polynomial, then s must divide a n and r must divide a 0. You don't really need to use this technique a lot. We don't really use this a lot, but it's also very useful. It's a very useful technique. You can reduce the number of checks that you need if you really needed to use this. But the last one is probably one of the more important ones. So if P of X is irreducible, then so is any shift. So if we shift it by some constant along the x-axis, then if Q of X is irreducible, so we kind of bring everything together and we kind of talk about not just polynomial rings, but polynomial fields. So a polynomial field is really just an extension of what we already established in the integer case. So remember that if we consider ZP is just the integers modulo P. So we can also write this as Z mod PZ. And this is the same as saying Z modulo P. So if we consider this property that we've already established in the previous chapters, then this is a field, right? Provided that P is obviously a prime. So we can extend this notion to a polynomial field. It's just that P is irreducible in the sense that it can't be written as a product of integers smaller than P in polynomials. A polynomial that is irreducible can't be written as a product of polynomials of less degree. And so you can kind of make the analogies between integer fields and polynomial fields. And so we say that f of x, the polynomial rings, so dealing with abstract algebra stuff, but the idea is that this is just a quotient. This is really saying, that we're going to quotient out f of x, and then we're going to consider all of the elements in this field. So we're going to consider all elements in this field. The technical term for this is that f of x is an ideal, but it's modulo to signify that f of x has a very special property in this field here. But you don't need to know specifically why we write it, but if you're interested, there are some other courses that you might like to fields like this. It's the same idea. It's really just a quotient. So if f of x is irreducible, then we say that this is a field. And if we have a field, then we have a field of a specific number of elements. So n to the power of the degree of the polynomial is the number of elements in your field. So we'll go through some examples of this. Oops. So the first question is, we want to show that this is irreducible. And we want to explain why it's a field of 8 elements. So the first part is to show that this is irreducible. So notice that the coefficients are all 1. So this is what we call a primitive polynomial. And so because it's primitive, we can just use technique 1. It's a primitive. So what this means is that there's a degree, there is a factor of degree 3/2 or less. But the only possible way for this to happen is if we have a linear factor. So there must be a linear factor. So the only possible linear factors in this field, or in this ring, is x and x plus 1. There's no other possibilities. There's no other possible degree 1 polynomials. But we can see that f of 0 equals to 1. So the reason why we set f of 0 is because this would imply that x must be a factor. So f of 0 refers to x, f of minus 1 refers to x plus 1. Yep. But we can see that f of 0 is 1 and f of minus 1 is not 0. So both of these are not 0, meaning that x and x plus 1, well, they can't be factors of f of x. So what that means is that f of x has no linear factors, which implies that it has no linear terms. It implies that there are no quadratic factors as well. And so f of x must be irreducible. The element. So we start off with the constant terms. There are only 2 possible constant terms, 0 at 1, x plus 1, x squared plus 1, x squared plus x squared plus x plus 1. And if you count that, you'll have 8 elements. You'll have 8 elements. And that really comes back to this idea of a field of a defined number of elements. So I'm just going to skim through it because we're running out of time. And I kind of want to cover finite fields a bit more because it's pretty important. So again, it's a field if and only if this is irreducible. So to prove that f of x is indeed irreducible. And so what that means is that we need to show, well, we can use technique 1 again because this is a primitive polynomial. And so it must have a linear factor, but you can easily check that it doesn't have any linear factor, which immediately implies that it has no quadratic factors either. And then as a result, it's irreducible. And because it's irreducible, f is a field, and it's specifically a field with 2 to the power of 3 elements. Cool. I'm going to skim through this. Okay, I'll cover the proof for M3 being irreducible, but I'll let you read the irreducibility proof for M1. M1 is the same idea. This time, we need to consider 2 separate cases. We need to consider linear factors and potentially quadratic factors as well. But it's not too bad. But I want to cover the irreducibility for this one because this one's an interesting one. You can do it the original way, but we're going to do it slightly differently. We're going to show that M3 of x is indeed irreducible, and we're going to use Eisenstein's criterion for this. But we're going to do it in a way, in another way first. So M3 of x is equal to this geometric series. Every time you see a geometric series, think the shift is irreducible. By virtue, it means that the original polynomial is irreducible. Okay, so we're going to shift everything by 1. And what that means is that the bottom term here will vanish to x. So it won't become x minus 1, but it will become x. But the top will become x plus 1 to the power of 5. So in the end, we get this expression here. Remember that we just substitute x plus 1 wherever we see x. Okay? And then we can expand the top by using the binomial expansion. And then we get this. And the good thing about this is that the 1's will cancel. The bottom here will cancel to x. And we get this nice expression here. Is by choosing p equals to 5. And the reason why we chose p equals to 5 is because we noticed that the term here is divisible by 5. So each of these coefficients is can be reduced by 5. Well, 5 is a factor across every single one of these terms. So p equals to 5 seems like it works. So p divides every coefficient except for the leading, and hence we have shown that M3 of x is irreducible by using a shift and then applying Eisenstein's criterion. So a takeaway message here is every time you see a geometric series, something like this, you should always think, can I apply a shift and then Eisenstein's criterion work out? Cool. All right. So I'm going to skip this. State the number of elements. Well, the number of elements is really just 2 to the power of the degree. So 16. It's quite straightforward. And now I'm going to skip this one as well. So I'm going to move on to finite fields. If you have any questions, feel free to just put it in the chat, but I'll probably go over it towards the end after we cover the last chapter, because the last chapter is quite important. Okay, so a finite field. So we kind of have already developed this idea of a field. So a field of polynomials is just a polynomial in which you quotient out this m of x term. And remember that m of x needs to be irreducible in f of x in order for it to be a field. So m of x being irreducible implies that this is a field, and this is a field implies that m of x is irreducible. Okay, so we're going to kind of use this idea to finally construct what we call finite fields. All a finite field is just a field with finitely many elements. So you might have fields that have infinitely many elements, but that's not what we're looking at today. We'll be looking at fields with specifically finitely many elements, and then we're going to see, are there any characteristics of of these fields that we can extract? So Moore's theorem basically tells us the complete classification. Every finite field is isomorphic to, they might have different addition and multiplication tables, in which case they are slightly different, but from a classification and construction point of view, if we were to just construct the fields, there is no distinction between the two. So every finite field can be sort of decomposed into, and it's important that m of x is irreducible in zp of x. If it's not, then it's not even a field, in which case it can't be a finite field. So it's important that this is a field in the first place. Well, okay, so finite fields can be interchangeably referred to as what we call Galois fields. So a Galois field is just a finite field, or a field with finitely many elements, and we denote it by gf of q or f sub q. And we've already seen how many elements this sort of field has. This field has p to the power of the degree of m of x, many terms. In which case, every finite field will have this many terms, depending on the structure of your isomorphism. So it's not that finite fields can be any type of size, but rather it has a very specific type of size. It has to be some prime to the power of, it has to be p to the power of some k, where k can range from 1 to n, I guess. Cool. So the key takeaway here is that every finite field, so finite fields, have to have this type of form here. So something like Z4 is not a field. It's not a finite field. It's not a field to begin with. And yeah, so we write it like this. So this symbol here is just the isomorphism field, the symbol. But you don't really need to know anything about isomorphism. You don't really need to know what it means, but rather that any finite field can be written in pretty much this form, or can be written closely represent this form here. Cool. So the order of finite fields, remember that you can't have any arbitrary number of elements in your field. For example, is a finite field because it's a field of characteristic 2. Z4 is not a finite field because Z4 is not a field. Remember that a field, if we're specifically just talking about integer fields, this bottom term here needs to be prime. So because it's not prime, it's not a field to begin with. But in saying that, there are finite fields with 4 elements, and they have characteristic 2 because, well, it's 2 to the power of 2. Z13 is a finite field because 13 is prime. So it's a field and it has finitely many terms. Hence, it's a finite field and it has characteristic 13. The order of elements in your finite field has a very specific structure. So if Q is a field of Q elements, then this group or this field of units has Q minus 1 elements, because remember, we disregard the 0 element. So remember the number of, the set of elements which have a multiplicative inverse. And so 0 never has a multiplicative. So that's a way in which we can tell whether or not something has, or what sort of order an element has. Okay, so this one came from last year's paper. So which of these numbers can be cardinalities of finite fields? Cardinalities means size, so don't be too scared of the word cardinalities. That's just the size of the field. Well, remember that every finite field is isomorphic to this, something like this. So the only way for you to possibly have a finite field is if you have cardinalities of powers of primes. So we look at this and we're like, okay, 2 is a power of a prime. 7 is not a power prime, so you can't ever have finite fields with 7 elements. It works, and 19 does not. 19 works as well. Yeah, I forgot to put 19 here, but it should be 2, 9, 16, 19. Cool. And then let f of x equal to this. Prove that f is a field. Okay, we're going to skip this part here. So remember, to recap, to prove that it's a field, we just need to show that f of x is irreducible in Z2. But we're going to look at number 2. So the question asks in F star. So to do this, we kind of want to look at the powers of, well, we want to look at the factors of 7, because the possible number of elements is 8, so 2 to the power of 3. So F star has 8 minus 1, which is 7 elements. So the order of elements must divide 7, and so the possible orders are either 1 or 7. So you can't have 2, 3, 4, 5, or 6 as an order. Cool. And then now we're going to look at specifically looking at elements with order 7, or more specifically, order cube minus 1. 7 is not really that important. It's not that special. We're going to look at elements with order q minus 1. And we call these primitive elements. So we're going to look at a primitive element, and then we're going to look at minimal polynomials as well. Hopefully I'm not going too fast, but I kind of want to go. I want to go over BCH codes as well. So I'm going to kind of skim through it. These slides will be available to you, I think, a few days after this live stream as well. So an element alpha is a primitive element if the order of alpha is q minus 1. That's pretty simple. That's just a definition. We've already seen this before. Whenever we're talking about primitive elements of integer rings. Okay, so now we go over to the minimal polynomial. So the minimal polynomial is a monic polynomial of smallest degree where alpha is a root. So it has to be that alpha is a root, and it's a polynomial of smallest degree. And if that is the case, then we have a minimal polynomial. Okay, so if m of x is irreducible and m of alpha is 0, then m of x is the minimal polynomial. And that makes sense, right? Because if m of x is the minimal polynomial, then it is the polynomial of the smallest degree, which implies that m of x must be irreducible. Otherwise, we can factor it into a product of polynomials. And because m of alpha is 0, what that implies is that m of alpha must also be a root of at least one of the factors. So we ensure that m of x is irreducible, which implies that... Okay, so let alpha be a root, and then we're going to determine whether alpha is a primitive element, and then what are the possibilities for the orders of the elements. So here we define Z3 of alpha to be this field, and we're going to determine whether alpha is a primitive element. So is there only one minimal polynomial? You can certainly have multiple minimal polynomials for, I guess, that's a good question. I think minimal polynomials, I think, are unique, actually. So you can only have one minimal polynomial for alpha, and same as any power of alpha. So it is not just a polynomial, minimal polynomial. It is so you can see the minimum polynomial. So there's only one minimal polynomial. Yeah. So is alpha a primitive element? So remember, for it to be a primitive element, we require that the order of your primitive, or the order of alpha is q minus 1. So here you have 3 to the power of 3, which is 27. So the order must be 26. So we're going to show that alpha has order 26. Know that alpha is a root of this polynomial. It means that alpha to the power of 3 plus 2 alpha plus 1 equals to 0, and 1 on the other side. We get alpha cubed equals to minus 2 alpha minus 1. But because we're working in Z3 here, we can just add 3 alpha and 3 to both sides, and we get alpha cubed equals to alpha plus 1, 2. Okay? So now we're going to start finding powers of alpha. So we know that the order of the element must divide the order of this, right? So we need to find the order of Z3 of alpha first. But this is a finite field, so it has order 27. So 3 to the power of 3. So we need to find we need to consider orders of 27 minus 1, which is 26. So we just need to check 2 and 13. If neither one of them are successful, then we know that the order must be 26. So instead of looking at all 26, we can just look at 2 and 13. And once we know that 2 and 13 are it's not 0, then alpha to the power of 26 must be, 26 must be the order. Okay? So, well, first of all, alpha squared is easy because alpha squared is just alpha squared. It's not 0, or it's not 1, sorry. So we know that the order cannot be 1 to see whether 13 is the order. So to do this, we kind of need to think about how we might like to break up alpha to the 13. Well, alpha to the 13 is alpha to the power of 3 to the power of 4 times alpha. And you can check that this is true. Well, the good thing about this is that we already know what alpha to the power of 3 is. Alpha to the power of 3 is alpha plus 2. So we can just write alpha to the power of 3 as alpha plus 2 to the power of 4. And then we multiply by alpha. We can expand this out using binomial expansion. We simplify it. Remember that we're working in modulo 3. So you can simplify it. You can re-express everything in terms of alpha to the power of 3 to 1 and 1. And then we get to a point where we get to this point here. Alpha to the power of 3 plus 2 alpha, which is alpha plus 2 alpha, which is 2, right? Because alpha plus 2 alpha is 3 alpha, which is 0. So we're left with 2. But 2 is not 1. So alpha to the power of 13 is not 1, in which case 13 is not the order of alpha. So that means the order of alpha must be 26. And you can check. Alpha to the power of 26 is just alpha to the power of 13 squared, but that's 2 squared, which is 4, which is 1. So alpha is a primitive root, and the possible orders are 2, 13, and 26. So quite straightforward. We just know of these types of roots. This is pretty important, and it's quite difficult to kind of grasp, but hopefully it kind of makes sense towards the end. And then we'll cover BCH codes. So we know that alpha is a root of x to the power of 3 plus x plus 1. So we need to find the minimal polynomial of alpha squared plus alpha and alpha squared plus alpha plus 1. So the first thing we want to do is we want to basically think about how we might like to construct alpha squared plus alpha. Well, we know alpha is a root of x to the power 3 plus x plus 1. So what that means is alpha to the power 3 plus alpha plus 1 is 0. But that implies that alpha to the power 3 is alpha plus 1. Remember that we're working in Z2. So we're working in modulo 2. Okay, so if we multiply both sides by alpha, then we get alpha to the power of 4 equals to alpha squared plus alpha. And then we multiply both sides by alpha again, we get alpha to the power 5 is alpha to the power of 3. So alpha to the power of 3 plus alpha squared, but that's alpha squared plus alpha plus 1. So in other words, we're finding the minimum polynomial of alpha to the power of 5. So for simplicity, we're going to let beta equals 0 and h of gamma equals 0 as well. So we're going to basically find some linear combination of powers of beta for which when you add them together, that equals 0. And we're going to do the same thing with beta, with gamma. So to do this, we will construct a table of powers for alpha. So we notice that alpha is a root of this polynomial, which is irreducible in Z2. You can check that for yourself. And because of this, you know that you will have 2 to the power of 3, which is 8. 8 minus 1 is 7. So you know that alpha to the power of 7 should be 1. And that's what you should be thinking in your head. Okay, so we just kind of construct it like this. This is our table of alphas. The next thing we want to do is we want to find powers of alpha to the power of 4, right? Because that's what your beta is. So beta to the power of 0 is 1. Beta to the power of 1 is alpha to the power of 4, which is alpha squared plus alpha, just by looking at this. Beta squared is alpha to the power of 8, which is, well, it's alpha to the power of 7 times alpha. So that's alpha. Beta to the power of 3 is alpha to the power of 12. And then that's, well, 12 is 7 minus 5. Oh, it's 7 plus 5. So it's the same as alpha to the power of 5. Alpha squared plus alpha plus 1. And you can see that if we add these together, alpha squared and alpha squared will cancel. Alpha, wait, let me see. Okay, so if you add beta cubed with beta, then you see that alpha squared will cancel, the alphas will cancel, and the ones will cancel. So beta cubed plus beta to the power 0 will give you 0. So beta is the root of this polynomial here. And you can see that no other combinations of beta, powers of beta, will give you 0. And so that's how you can tell that this is your minimal polynomial. Cool. And it's basically the same idea. I'm gonna skip this, but you can check for yourself. Once we get up to here, we can kind of stop because, okay. So we're going to quickly go over this question. So let f of x be this polynomial. We want to show that it's irreducible, find number of elements, and then we're going to basically do this. So I'm just going to skip this for now because you can kind of do it yourself. We're going to go over this times 1 plus alpha gives you 1. Well, if we look at our polynomial, remember that alpha is the root of the polynomial. Well, we can rewrite our polynomial as x squared times x plus 1. But what that means is that if we consider f of alpha, remember that f of alpha equals to 0. In other words, alpha squared times alpha plus 1 equals to 0. In other words, alpha squared times alpha plus 1 equals to 1. And so we found a specific a, so that when you multiply a with alpha plus 1, we get 1. In other words, alpha squared is the inverse of alpha plus 1. And that's how you can do it in general. For part B and part C, we're going to set up a table of powers. I'll let you check this for yourself, but this should be correct. And then by the previous table, we have that 1 plus alpha squared is nothing but alpha to the power of 4. 1 plus alpha is alpha to the power of 5. So we get alpha to the power of 4 divided by alpha to the power of 5, but that's just alpha to the power of minus 1, which is alpha to the power of 6, because alpha to the power of minus 1 is nothing but 6 minus 7, but alpha to the power of minus 7 is just 1, because the inverse of alpha to the 7 is, well, 1. So alpha to the power of minus 1 is alpha to the power of 6. And yeah, and that's how we can do part C. Alright, so I'm going to kind of skip over this question. So I might go a bit over time, but we're going to cover BCH codes. Just because it's pretty important, and it's it pops up a lot in your past papers as well. So we're going to cover BCH codes, encoding and decoding 1 error, and then we're going to cover 2 errors as well. So the slides will be available to you after anyway, so it's fine if I just kind of skim over a few of the questions. And then if you still have questions, I'll be available for a few minutes afterwards to kind of answer your questions. Okay, so BCH codes. So the idea with a BCH code is that it's a more versatile code, because it allows us to be able to correct and detect multiple errors. So instead of looking at just 1 error, we can correct 2 errors or 3. We basically take our values, and we're going to just send that as the coefficients of our polynomial. So we're going to construct a polynomial where the coefficients are taken by the values of the message. Then afterwards, we're going to construct a sum of polynomials. So it's going to be the information polynomial plus some remaining polynomial, where the remaining polynomial ensures that our m of x, so our m of x here, divides into c of x. And from there, we can encode using coefficients. I will go over, I think that we have an example. Okay, so as an example, we're going to encode this 1101. So the first thing we want to do is see that A6 is 1, A5 is 1, A4 is 0, A3 is 1, plus A1 of x plus A0. And then we're going to construct this in a way where f of x, which is this term here, divides into c of x. C of x with A2, A1, A0. Because we're working in Z2, if we add these two terms together, then this entire expression here will vanish, because when we add them together, we get this entire thing to be 2 times whatever this is, and that's 0. And then we get this remaining term here. And so that's the idea. So to retrieve the unknown coefficients, we just need to long divide ci of x by f of x. And then we get that ci of x is equal to x to the power of 3 times x to the power of 3 plus x squared plus 1. And you can check that for yourself by taking the x to the power of 3 as a common factor. And then x to the power of 3 plus x squared plus 1 is our f of x, indeed. So this means that d of x needs to be chosen term here. So we can skip x to the power of 4. Then we have x to the power of 3, x to the power of 2. We don't have an x term. And then we have a 1. So this is our r of x. And then we're going to write r of alpha equals to alpha to the power of 6 plus alpha to the power of 5, 3, 2, and 1. Now remember that alpha is a primitive root of m of x, meaning that we need to consider the table of powers. So because we know m of alpha equals to 0, then we have that alpha to the power of 3 equals to alpha squared plus 1. Remember that we're working in modulo 2. So we're going to construct this table of powers from 0 to 7. And then we're going to kind of compare these terms here. So alpha to the power of 6 is alpha squared plus alpha. Alpha to the power of 5 is alpha plus 1. Alpha to the power of 3 is alpha squared plus 1. Alpha squared plus 1 is just alpha squared plus 1. So if we simplify it, let's have a look. So alpha squared, those two will cancel. Remember that we're working in modulo 2. Alpha will cancel, and the 1s will cancel. So all that's left is 1 plus alpha squared, but that is just alpha to the power of 3. So we know that an error has occurred, and it has occurred as specifically at the alpha to the power of 3 term. So what that means is that an error has occurred precisely at A3. So the correct message should be 1100-101 instead of 1101-101. And then we decode it by taking the first four digits. So we take 1100, and that's how we can decode it. So decoding and encoding using one error is actually really straightforward. We're going to look at decoding using 2 errors. I'm going to encode them as well. So that's the reason why BCH codes are very powerful. We are able to extend the code to be able to correct 2 errors and 3 errors and so on, but we only really work with 2 errors. So it's a little bit more complicated because we can't simply we start off with a polynomial m1 of x. Usually it's given to us, and we know that alpha doesn't work because the minimal polynomial of alpha is the same as minimal polynomial of alpha squared. So usually we'll be looking at alpha to the power of 3, and for this course I believe we're only looking at alpha to the power of 3. And then the resulting polynomial is just the product. And this comes back to something that we didn't cover in this workshop, but it's in your lecture notes, which is Gauss's lemma, meaning that if you have 2 primitive polynomials, you multiply them together, then you also have a primitive polynomial. And that's essentially what we're doing here. We're taking the product of these 2 polynomials. Okay, and that's going to be what m of x is. So to encode it, it is exactly the same process. So we're going to construct ci of x, we're going to construct d of x, and then we're going to encode it this way. But to decode it, it's a little bit more complicated. So to decode it, again, we're going to start the same way. We're going to construct our r of x and we're going to find r of alpha. If r of alpha is 0, we have no error. We're all good. Otherwise, we have at least 1 error. We don't know whether it's 1 or 2 errors. Then the next thing you're going to do is to compute r of alpha cubed. And if we know that r of alpha cubed equals to the cube of r of alpha, then there is 1 error precisely at the ith location where we have alpha to the power of 3i. Otherwise, if they are not the same, then we have 2 errors. Alright, so we're going to do this using this problem here. So we have m1 of x, m3 of x, and we know this construction here. We want to encode the message 110010 using the BCH code above. So again, to do this, we basically write out the information polynomial. So that's x to the power of 14 plus x to the power of 13 plus x to the power of 9. Then what we're going to do is we are going to find ci of x mod m of x. And that's going to be what r of x is going to be. So we can do this by long division. I'll let you verify that this is true. I believe this is correct. So all you need to do is just polynomial long divide ci of x by m of x. And then you get this expression here. So the first few terms are going to be it's going to be 11000010, so it's going to be exactly the same as this. So you can see that these terms here, these terms here are exactly the same as these terms here. The only thing that we need to encode now is just the coefficients of this polynomial here. So we can see that x to the power of 7 is going to be 1, x to the power of 6 is 1, x to the power of 5 is 1. There's no x to the power of 4 term here, so it's going to be 0. And then we have 3, 2, 1. So all of these terms are going to be 1. And then we finish with this encoding message here. Okay. And then to decode it, we have we need to kind of consider a few things. So the first thing we need to do is to find r of x, and then we need to find r of alpha and r of alpha cubed. So the first thing we want to do is to construct r of x. So this is just given by the coefficients. So this is just a polynomial constructed by the coefficients of your message. So there is no x to the power of 14 term, no x to the power of 13, no x to the power of 12. So we start off with x to the power of 11, 10, 9, and then we have no 8, 7 term here, and then we have a 6, 4, 3, and a 1. So that's how we construct r of x. R of alpha is going to be a term where alpha is the primitive root of m1 of x. So it's going to be the root of m1 of x. M1 of x is given to us by x to the power of 14 plus x plus 1. So in other words, we have that alpha to the power of 4 equals to alpha plus 1. Remember that m1 of alpha equals to 0, which implies that this is equal to 0, which implies that we have this. Okay, so what we're going to do now is we're going to construct a table of powers to find alpha to the power of 11, 10, 9, blah, blah, blah. And so this is what we're given. This is what we know. Then we just basically compute it. So it's just a bit of algebra. We just compute, and then we get to alpha to the power of 8. So that is going to be what your r of alpha is going to be. Then we compute r of alpha cubed. You do the same thing. So here, notice that this is alpha to the power of 33, but then you take modulo 15 because this cycles every 15 times. So every time you hit 15, you go back to 0. And so you just take the modulo with respect to 15. And so 33 becomes 3, 30 becomes 0, 27 becomes 12. 18 becomes 3, 12 becomes 12, 9 becomes 9, and then you have a 1 left over. And notice that because we're working in modulo 2, this and this will cancel. Alpha to the power of 0 is 1, so these two will cancel, and these two will cancel. So, in other words, r of alpha cubed is alpha to the power of 9, but notice that r of alpha to the power of 3 is not the same as r of alpha cubed. And so we have two errors. And then you can repeat the next question using the exact same method. And yeah, and that's basically the end of the workshop. Hopefully you guys have found it helpful. I will stay back for a few minutes if you guys have any last minute questions. But otherwise, good luck with the exam, and hopefully everything goes well. All right, if there are no more questions, then yeah, best of luck. So someone asked, when will the slides go up? So the slides will be up hopefully by Monday. So I'll try to get them up by Monday. We just need to do a few